Okay, so it's officially recording. I'm just going to give people a few minutes. Is everyone doing okay in all of this, this mess? I hope that nobody is sick or too stressed out. Let's see, it's 12:05, so I'm about to get started. I'll just introduce you guys to my colleague. That's Lola. She's going to be joining us for class today. Hopefully she will not be a disruption, but if she is, she's going to have to get kicked out. So she's here to learn about linear regression as well. Let's see, some people, ooh, Jessica's working at the hospital. Thank you, Jessica. You work with your mom? Oh no, you have to get tested. My brother had to get the COVID test, and it goes like, that's the one I think that goes all the way to your brain, basically. It's not fun. His test results came back negative yesterday, so we were really excited. I need to sit down. I need to go on. Let's see how this is going to be. Okay, so I'm going to attempt to share a screen with you. Oh, no. We don't. Say bye to Lola. She got to go. Nope. Right here. What happens is, as soon as I start talking on FaceTime, then she thinks it's about her. So I'm just going to put her in there for the next few minutes while we get this done. So I'm going to attempt to share a screen with you. It's a whiteboard app. As you know, I like to use the whiteboard a lot. So I'm trying to keep this somewhat similar to how we would do this in class. We'll see if it works. We'll see if it works or not. So if I share this screen with you through my iPhone, I'm attempting to write with a digital pen, so it's taken some practice. I'm gonna do AirPlay. Then I can, whoops, nope, that's not what I want. And then you guys may be able to see this screen. Can you type into the chat maybe and let me know what you can see? And I'll try to find a way to pull the chat back up. Now I can't see it. There it is. Okay, so it's small, so what I'm gonna do is zoom in on it at different times. It's really obnoxious, like the way the app works. So basically, like if I zoom in like this, you can probably see better. And I'm just gonna kind of move around on the board and stuff, and we'll kind of work through some example problems. So I see from Jessica and Tabitha that you guys can see this whiteboard. So if no one can see, then let me know. I'll try to monitor this chat window over here. I'm gonna put this right here and get this screen out of the way. Ooh, there's a lot of work going into this. Okay, so hopefully you all saw the review sheet that I posted under week 13, and then maybe also I posted it on Canvas under exam and review guides under that tab. So what I'm going to do today is just kind of go over each of those points so that you can prepare for exam 3. Does anyone have questions about the updates or changes to the class before I start talking about this? If you want, you can type them in, or you can unmute yourself if you want to ask questions. Or you can also, there's an option to raise your hand, I think, and I can call on you. So if anyone has any questions about like the updates that I posted, you can type them in. Basically, this exam is going to be available for you to complete anytime. So technically it's already available. So like after you get off this call, if you're like, oh, I'm totally good, I'm prepared and ready to take this, then you could go ahead and log in to Canvas and pull up the exam. If you're not ready to take it and you need time to study, I've recommended that you complete it by Friday to stay kind of on a reasonable timeline for yourself. But as I mentioned in the video updates I announced earlier this week, it's not going to be due until April 24th. And so the rule was, as I start updating assignment due dates in Canvas, you'll see that everything that was previously due is now going to be due on April 24th. And will be available for you to submit anytime between now and then. So if you missed past assignments, you could go back and submit those. And as long as you submit it, yes, I am posting this to Canvas, responding to Cody. Oh my gosh, the cat is screaming. Oh, joys of working from home, social distancing. So anything that has a due date prior to April 24th is now going to be moved to being due to April 24th. And for your class, that means that you will get the 5% extra credit reward for turning things in on time, as long as you submit those things by April 24th. And what I'm going to do is try to go through on certain days of the week. Right now, I expect that might be Thursdays or Fridays, and just update grades on a regular basis. Based on whatever you've submitted that week. Then for your exam 4 and your optional final exam, which you don't necessarily have to take, review the syllabus if you've forgotten that, but it's basically 22 points of extra credit to help boost your grade. The exam 4 and the optional final exam, their due dates were already after April 24th, so they'll stay the same. So this exam, I recommend you complete it by Friday, but you have until after that if you need more time to prepare and review. So on the review sheet, I gotta let the cat out. That's gonna be distracting me. You better act right. It's not even playing. Sorry about that. Okay, so on the review sheet, you see that the exam is going to be divided into 2 sections, one focusing on the concepts of simple linear regression, and the other focusing on application of those concepts, basically doing problems like what we did in activity 6 to make sure you understand how regression is done. So the first questions, it's a little bit different since we're doing this virtually, so I'm just gonna kind of give you the answers rather than having you work on them together or discuss them. So the first question is, what is the simplest linear model that we talked about in class? So since it's been a while, you will probably see some reference to this back in your notes, but what I'm referring to here is the y-average. So I mentioned that when you're making predictions about a variable and you don't have any other information other than the variable that you have measured, the simplest prediction you can make will be the mean of that variable. So for example, this might be a point where I write on the board. Let me zoom in a little bit. I don't know why my screen isn't updating. What if you don't stop? All right. So if I take, if I observe a variable y and I call it your exam 3 scores, right? So we'll just say exam 3. Can everybody see this, what I'm writing? And let's say that I'm just going to give an example of like a small sample of 3 people where we have individual 1, individual 2, and individual 3, right? So the reason why I'm going through this example is because I might ask you on the test to calculate an average in relation to this question. So if I ask you, you know, what's the simplest prediction you can make given this y variable, scores on y that I've given you? It's been a while since we worked with raw scores, but really all you would have to do is just calculate the average of that variable and say, I don't know anything else, but I know you come from this sample of data, I'm going to predict you scored the average. So if I have a person who scored an 85 on exam 3, a person who scored a 90 on exam 3, and a person who scored a 95, then you would just say, well, the simplest prediction I can make for any person taken from that sample, no matter how large it is, just happens to be 3 people, you would calculate an average by adding up all the scores, right? It's as easy as it sounds. And dividing that by 3 people, which gives you an average score of 90. So if you don't know anything else, what you could predict is that people would score a 90% on that test. If I ask you, and I'm really clear about this on the test, so when I say like, don't worry about z-scores, I've just given you these data and raw scores so that you can give me your simplest prediction in terms of the original scale. So 85, 90, 95, or whatever percent. That means just calculate the average of those numbers, right? What we had been doing in class, because we're working with linear models now, is just using z-scores. So if we were to use the z-score transformations of this variable y for exam 3, I can tell you how that calculates. It ends up that person number 1 has a z-score of exactly -1, so 1 standard deviation below the mean. Person number 2, since the average was 90, they have a z-score of 0. Sorry, my pen went off. And you might guess person number 3 has a z-score of 1. So you won't have to go through the process of calculating any of that. This is just for demonstration purposes. So when you're dealing with a z or a standardized distribution, the mean of that distribution is always going to be 0, right? Because you add all these numbers together and they sum to 0. So when you're talking about that average, the simplest prediction you could make would be 0. But in terms of the original scale, if I don't give you z-scores, you would just say, well, I'm just going to calculate the average then. When you're dealing with standardized scores, you just always have the luxury of knowing, well, the simplest prediction I can make is the average. And since I'm dealing with standardized variables, the average is going to be 0. So when we were doing, let me zoom out. When we've been doing simple linear equations using this equation right here, we've been using a standardized equation, meaning we've been using standardized z-score values for x to insert and predicting y also in terms of z. And so when you look back over, I think it's your activity 6, it says like, what is beta 0 representing in this equation? So that's this term here. Essentially, that is representing the y average or the constant. They're the same thing, the intercept also. So because this equation is standardized, when we end up going through these example problems, we're just going to insert a 0 there for each person because we're dealing with the z-score distribution of y. But in reality, what that 0 is representing is the raw average. So if I were to refer back to the exam scores, that's the person who scored a 90, right? Any questions about the simplest prediction you can make? So it's basically saying, like, we don't know X, we don't know correlations with other variables, so we can't do a full linear equation. We just know what we've observed. Therefore, I'm going to predict that everyone in my sample scores a 90. And as you know, like, some people, that's not true. Some people scored 85. Maybe some people scored 91, 92. There's going to be a degree of error around that, but it's still the best prediction that you have. And it's simple to calculate. So the next question in the review sheet, I'm just checking for comments to see if everyone's good, is when would I use the mean of y to make predictions? And you could just think of that as, to summarize what I just said, if you don't have information about any other variables that correlate with y, or similarly, thinking about this linear equation, when x equals 0, let me give the screen a chance to catch up. It looks like it's frozen. Not sure what it's doing, but I'll just say when x equals 0 in the equation, you're going to end up predicting the y average. Or if you don't know anything about the correlation, or if you don't have a measured correlation, you're going to just predict the y average. So that's when you would make, when you would use the mean to make predictions. How can we improve our predictions of y beyond the mean? So essentially, that's what the simple linear regression is trying to do. It's trying to improve upon the simplest prediction by adding more terms, more algebraic terms or linear terms or whatever you call them, into the model. So my screen is frozen. I don't know if yours is, so I'm gonna stop sharing and share it again so that it updates. Sorry about that. Technical difficulties, my apologies. Let's see how this is gonna be. Oh no, Sukaina got kicked out of the meeting. Did anyone else get kicked out? Sukaina, you good? I'll post this video at the end in case you think you missed anything. Cody says he did not get kicked out. Ooh, stress. Okay, so can you guys see this screen that I've shared again? Last thing you heard was the answer to the second question. Awesome. Then my screen froze and went down, so you didn't miss anything. So I think you're good. Oh, Jesus. Okay, so let's see. How can we improve our predictions of y beyond the mean? That's the third question. So the simple answer to that is you can observe some other variable, such as x, that you think might be related to y, and then model that relationship in a simple equation, or even any kind of equation in a predictive regression model. So that is essentially what we have done here, and that we have added the term or the variable x and also accounted for the correlation between y and x, and that's what's represented here as beta 1. So essentially we're just adding that information to the simplest prediction that we already had, right? You cannot make your predictions more precise, no matter what you're trying to predict, if you don't know how that variable relates to something else. So essentially, if you want to be more precise or improve your predictions, you have to account for other relationships and correlations with other variables. Does that make sense? All right. Just double checking that everyone's with me. Okay. What does the line of best fit represent? So that is something that refers back to your activity 6 and also those 2 readings that I assigned for activity 6. Basically, the line itself represents y-hat values that we have calculated from our regression equation. So you remember maybe like I went through that example in class of graphing the line of best fit, and all of the y-hat values fell on a straight line, right? That straight line is representing an infinite continuum of possible predictions for y in either direction, right? So it's kind of saying like, given any score on variable x, this is what you would predict for y. So the line of best fit is simply your regression model. It's like a visual representation of that, and it represents predicted y values or y-hat values. We use that line, or we use that linear model, because it is meant to minimize the amount of error for everyone in the sample. And so in class, we discussed a couple weeks ago, like there are alternative nonlinear models you could use that use curves, or like a S-shaped function, something like that. Those lines, those curvilinear lines, they do a good job of minimizing error for some people, but not for everyone in the sample. This simple linear regression line does a good job of minimizing the amount of error on average for everyone. So that's why we use that linear model. That's why it's called least squares estimation. It's basically saying like you have the least amount of squared error with this method. So study tools for these kind of concept checks that you might want to review would be the questions from activity 6. So go over the conceptual questions from the beginning of the activity. And if you are waiting to get an activity 6 from me, I will double check that today, but you can shoot me a message as a reminder, and I'll grade that for you. If you need to, like if you haven't completed your activity 6 yet, then you can reference the readings on comparing correlation and simple regression and the reading on the line of best fit to answer those questions. But if you've already completed that activity, you should be fine to just use that as a study tool for this. So section 2 is going to be talking about those applied problems on the back of this review sheet. The first point, first and foremost, know the notation for a simple linear equation. So that's simply what I've already been referencing here. The beta 1 times whatever the individual score on x was, plus the constant or beta 0 in the equation. So make sure you know that notation. know how to predict variable y. In other words, know how to predict or calculate y hat values from that equation when I've given you information about variable x. And I know like it can be helpful for you to practice interpreting those predictions in your own words, but I'm not going to ask you to do that on the test. That is more practice that will kind of hopefully help you learn and remember this material for later. So if we look on the second page of this review sheet, I've given you example problems, and this is like what you would see on the test. So I will give you the correlation and a sample size. I'll give you individual scores on X and Y, and then you'll kind of take it from there. So I say, assume that we have collected another sample of data, and that's what I'm essentially working with here. So I've already written this out on my little whiteboard where we've got 5 people, we've got their z-scores for variable X, which is LAPD trust, so how much they trust the LAPD, probably on a scale of 1 to 5, and variable Y, which is OJ guilt, probably measuring the extent to which they think he is probably guilty or probably not guilty on a scale of 1 to 5. Assume that higher scores indicate probably guilty. Assume that higher scores on variable X indicate, I think they're pretty trustworthy, right? I will provide the data and the correlation so that you don't have to calculate any of that, and you don't have to calculate z-scores or anything. So in this example, the correlation is -0.2. So what that means is it's a relatively weak-ish negative correlation between X and Y. So that still implies that the variables are deviating in opposite directions from their mean. So the more people tend to trust the LAPD, or those who tend to score above average on that variable, also tend to score below average on OJ guilt, or also tend to think he's probably not guilty. Does that make sense? Any questions about that interpretation? So what we are going to do is insert that correlation into a simple linear regression model to predict Y values for each person in the sample. So I note for part A, you're going to use data from table 1, and I'll give you a table like this on the test. And what I'll ask you to do is make sure that you can write out the linear regression equation for each individual so that I know if for some reason your predicted Y value is off, I at least know like, well, you knew how to calculate it. It must have been a typo or some kind of error, right? So I'll ask you to produce the equation you're using for each person. And so to that point, I kind of have to zoom in, but I'm using this data here. This is what you have in your review sheet, right? So for person number 1, the equation I'm going to use is going to insert -0.2 for everyone, right? Because that's essentially the correlation for the entire sample. So that part of the equation is going to be the same for everyone in the sample. So I could go ahead, come down here and say, I'm going to go ahead and insert the correlation into everyone's equation, -0.2. And what changes is their score on variable X, how much they deviated from the mean, whether they were above or below average. So for person number 1, you can see that they had a z-score of 1.07. So I'm going to zoom in over here. Hopefully that's good enough. And I'm going to squeeze in -1.07. Hopefully you guys can see that. For person number 2, they scored -0.53. So I'm going to insert that where X would go. And then for person number 3, they scored 1.07 on variable X. So you would come in here like so and say, okay, that's their deviation for LAPD trust. This person was 1.07 deviations below average on LAPD trust. And then person number 5 was almost half of a standard deviation. Sorry, my handwriting, below average on that variable. And again, I mentioned in this case, we're dealing with standardized variables, so the equation is standardized. So the constant, or the y-average, which is going to be the same for everyone because it applies to the entire sample, is just going to be 0. So I would still like for you to specify this part of the equation in your answer. I'm not going to count off if you don't, but sometimes it lets me know why there might be a mistake in your y-hat calculation. So essentially, this value is still here. So we're saying, like, in addition to the y-average, we would predict that a person would score the product of the correlation for the entire sample and whatever their deviation was on X. So when you go through and calculate that for each person, I'm kind of zoomed in, but hopefully you can see on your review sheet that you have that for person number 1, given the correlation and their deviation above average on X, you would say negative 0.2 times 1.07, and that gives them a predicted value of negative 0.21. And let me know, is the first, she says, the first individual negative 1.07 or 1.07. Sorry about that. It is, I'm double checking. Yep, it's 1.07. Crap. This is a little complicated. I wonder if I can erase it. Oh, yep, that was huge. Come back over here. Negative 0.2 times 1.07 plus 0, right? Is that good? The negative 0.2 is a correlation I gave you on the review sheet in response to Jessica. So she said, where did the negative 0.2 come from? So basically in the example problems instructions, I'll tell you the correlation between X and Y is negative 0.2. And that's something I'll give you on the exam as well. And then in response to Jessica's question, I corrected it to show person number 1 scored. This pencil keeps turning off. I don't understand. 1.07. Okay. So using those correct numbers, you would calculate a y-hat value of negative 0.21 for person number 1. For person number 2, you're going to calculate their predicted y value, or y-hat, by saying negative 0.2 times negative 0.53, and that's going to give them a predicted value of 0.11. For person number 3, you would say negative 0.2, again, times 1.07, like person number 1. So they're going to have a predicted y value of negative 0.21. For person number 4, I'm just saying negative 0.2 times negative 1.07, and that's going to give them a predicted y value of 0.21. And for person number 5, I'm going to say negative 0.2 times negative 0.53, and that will give them a y-hat value of 0.11. I'll give everyone a second. So what you will notice when I kind of zoom out on my whiteboard here is that these are their actual scores on variable y. We call this observed y, right? What they actually scored. Y-hat, which is why the little hat in the notation is important, is going to be usually a different value. There's going to be some discrepancy, between these. So for person number 1, they scored 0.88 z-scores above average on OJ-GILT, but the model predicted, accounting for the correlation, that they would have scored below average, exactly 0.21 z-scores below average on OJ-GILT. So not only was there some discrepancy, but it was actually in the opposite direction. Does that make sense? You can see the same applies to other, there's going to be some discrepancy for the rest of the individuals in the sample. So for person number 2, they actually scored, maybe I can use a different color. They actually scored, 1.07. The model, accounting for the correlation, predicted that they would score 0.11. So they scored below average on OJ-GILT, but we predicted that they should have scored slightly above average on OJ-GILT. The same applies, so for person number 3, they scored 1 standard deviation and then some below average on OJ-GILT. We predicted that they should have been closer to the average, still below average, but only 0.21 z-scores below average on OJ-GILT. For person number 4, they actually scored 0.88 z-scores above average. The model predicted that they would have scored above average, but it predicted that they should have only been 0.21 z-scores above average. So still a discrepancy. The model thought they would be closer to the average than they actually were. And then person number 5, we predicted that they would be 0.39 z-scores above average. But I'm sorry, that's what they actually scored. But the model predicted that they would have been 0.11 z-scores above average. So that is how you would calculate your y-hat values. And that discrepancy between y and y-hat is essentially the residual that we talked about. So the next point, so that was, that was point B on the review sheet. It says, using the data and the equations, calculate each person's predicted score for y. So we just did that by calculating y-hat. Then below the table on the review sheet, you see number 2, which says, think about how you would calculate error in our simple regression model. So like, how would we quantify that? And then to that point, calculate the squared residuals for each person. So that was one of the last things that we learned how to do. So the residual, not the squared residual, but the residual itself, it's also defined back in your notes. But a residual is the difference between a person's observed score and their predicted score. So you can make note of that if you're not sure where it is in your notes. A residual is the difference between a person's observed score and their predicted score. So the notation for that, I'm going to come over here because I'm about to calculate it, could literally be written out like so. A residual value is the difference between y observed and y-hat. Pen just went off again. And this residual is probably going to be different for each person. It doesn't have to be, but it usually is. So keep that in mind. So what you're going to do to calculate a residual is go down and say, okay, well, for person number 1, you would look over here and say, observed y was 0.88. Their predicted value was negative 0.21. So what's the difference between that? So what I'm going to go through, and you can do this with me or you can watch me do it, is I'm going to go through and calculate those differences for each person so that I have a residual score or a residual deviation, same thing, for each person. So here's how I'm calculating that, since you might not be able to see. Hopefully you have your review sheet. Person number 1, I would calculate their residual by saying their observed score, 0.88, minus their predicted score, which was negative 0.21. That gives them a residual score of 1.09. Of course, I'm running out of space on my tiny iPhone, but that's okay. For person number 2, I'm calculating their residual by saying their observed score on Y, so their actual score, negative 1.07, minus their Y hat value, which was 0.11. I'll put it in parentheses, but it doesn't matter. Gives them, a residual of negative 1.18. Making sure that no one sees any errors in my calculation. Feel free to type it into the chat if you do. Person number 3 had an observed score on Y. That's the scores I've given you, remember, of negative 1.07. And the predicted score that we calculated for that person was negative 0.21. And so their residual score is negative 0.86. For person number 4, their actual score on Y was 0.88. So I'm taking the difference between that and their predicted Y hat value, 0.21. I'll put it parentheses just because. And that difference comes out to 0.67. And for the last person, number 5, their observed Y score was 0.39 minus their predicted Y score, which was 0.11. And that gives them a residual value of 0.28. So these are just the residuals. They're not the squared residuals, right? I ran out of a little bit of room, but you can probably imagine to calculate the squared residuals. And the main reason I have you go through this is it's going to be relevant to the next thing we learn in the class. Calculating the squares will allow you to calculate a kind of error variance later. I'm not going to have you do that on the test, but I do want you to know how to calculate squared residuals. So what you're going to do is just square. Oh no, I deleted everything just now. There we go. Oh my gosh, minor heart attack. All right, let me zoom in so I don't do that again. Just trying to draw my exponents. I say square each of these residuals. And so as you go through and calculate those, what you will find, this would be the notation for squared residuals. It's also on your review sheet. You could write it out as Y minus Y hat squared. For each person in the sample, person number 1, 2, 3, 4, 5, right? So when you square person number 1's residual, you're saying 1.09 squared, that's going to give you a squared residual of approximately 1.19. For person number 2, their squared residual is negative 1.18 squared. That's going to give them a squared residual of 1.39. Person number 3, make sure I'm doing this right. We would calculate theirs by saying negative 0.86, there it is, squared, 0.74. For person number 4, 0.67 squared gives them a squared residual of 0.45. Person number 5, the last person, 0.28 squared gives them a squared residual of 0.08. So that's how you could calculate a distribution of squared residual scores. So make a note of that in your little activity there. Squared residuals. Pen went off again. Like, who designed this? Who wants their digital pen to turn off while they're writing? I don't know. Anyway, it's probably defective or something. Okay, that's how you would calculate squared residual scores. And as you can imagine, what we're going to end up doing in the future, maybe you can't imagine it, maybe you can't, but I bet you can. We're going to end up summing these squared residuals together to kind of calculate or quantify overall error in the sample. I think we might have done that in class, but we didn't focus on it. But to this point is all you need to know for the exam 3. So how to calculate y hat, how to calculate residual scores so that you can calculate squared residuals. That's all you'll need to know at this point. That's what the regression model, the simple linear regression model, will buy you. And of course, as I mentioned earlier, the point of using a simple linear model is that it will minimize these squared residuals to make them as small as possible for each person, particularly the straight line, the line of best fit, minimizes the average number of these values. So on average, these numbers should be smaller every time you add more information into your model, because what you're essentially saying is we're more precise. So because the correlation was so weak, in this example, it was negative 0.2, that's probably why some of the square residuals and some of the residuals themselves over here in this column were so large. Like, we had residuals of 1.09, that's more than a standard deviation, because these are still in terms of z-scores. We had residuals of negative 1.18. Those are pretty large if they're over 1. So you could kind of say, like, our model was not very precise. So the idea might be, in practice, like, could we add even another variable or something else that's more strongly correlated to minimize these numbers? Since in this example, the correlation was only negative 0.2, it's kind of close to 0, suggesting it may not be that useful in predicting how people feel about OJ. In this particular example, if I gave you a correlation that was negative 0.8, because they're more strongly correlated, you should notice that these residual values are smaller in that model, meaning you could be more precise by accounting for views of the LAPD when you make predictions about perceptions of OJ. Questions, comments, concerns? I'll give people a second. If you have questions, I'll stay on this call. I'll zoom out on this little whiteboard so you can see, like, all the things I drew on here. Sorry that they look so ugly. I will post the recording of this as soon as we get off the call. The cat is literally climbing the walls. You would think that she's in quarantine. I don't know. But if you guys don't have any questions and you feel comfortable doing these problems and answering these kind of questions, you are prepared for exam 3. So exam 3 will be very similar to the first two in terms of the layout. Most of them are going to be open-ended questions, and that means that I'll go in and double check your answers to make sure Canvas doesn't count off for a typo or something. So Jessica said, is there any specific notation we need to know? On the review page, I just noted that you should know, this is going to sound basic, but I just wanted to cover the bases. You should know what X and Y are, right? And be comfortable interpreting data for predictors and outcomes, like basically which columns represent which variables. Know what Y hat means, predicted Y values. So that's Y with the little hat on top. Know how to calculate the Y average and the notation for that, which most of you are comfortable with, hopefully all of you. The next notation on that sheet is this notation here. I'll zoom in. The difference between Y and Y hat, so that is just the residual score. I'm not going to ask you to define that, but you'll need to know how to calculate it, need to know what it is. And then the other notation on the review sheet is this formula here. The squared residual is essentially what that notation is representing. Or you could say it's the squared difference between observed Y and Y hat. But that is essentially a squared residual score. And then I'll review this really quickly just in case. You'll need to know the notation for beta 1 and beta 0. So as I noted on your review sheet on the second page, beta 1 is going to be the same thing as R, or the correlation between X and Y. In a simple linear equation like the one we're dealing with here, those numbers are essentially the same. But in practice, beta 1 is just referred to as a standardized regression coefficient. Because of the 1 attached to it, you know it is linked to the first predictor in the model. Now in a simple equation, that kind of becomes irrelevant because we only have one predictor. We don't have more than that. But that's essentially what that 1 is representing. The beta weight, or the beta coefficient that is attached to the 0 is always going to be referring to the constant. It's essentially saying, like, what is the coefficient when you have 0 information about anything else. So that's kind of referring, again, it's literally talking about the Y average. That's going to be the best prediction you start with. So beta 0 refers to the constant or the intercept, aka the Y average. Beta 1 is referring to the correlation between X and Y, or the correlation between Y and the first predictor in the model, which in our case is the only predictor. So that's all the notation that you'll need to know for this test. Other questions, comments, or concerns? I hope you guys can't see these embarrassing text messages that are popping up on my screen from my dad. He's just been interrupting the whole time. Thanks so much for signing on, and kind of the interaction has been helpful for me to, like Jessica pointed out, like, hey, that's a 1.07, not a negative 1.07. It's really easy for me to overlook some stuff like that, and kind of know like what questions you would have. So if you think of anything after you watch this video, for those of you who aren't here, you can send me an email or post on the Q&A forum on the Canvas website, and I will try to get back to those questions as soon as I can. Sukana says, will we review the last exam? Will you release the correct answers from the last exam? So, do you mean exam 2? Or do you mean yes, exam 2. We might have reviewed, I think you might have been sick that day when we had reviewed exam 2. But I will, let's see. Are you able to see, yeah, you had the flu. I think I can go back into your exam and make sure that I comment what the correct answers were. So if you have questions about answers you missed on exam 2, reach out to me and just say, like, hey, can you let me know what I missed on exam 2? And I will go back in there and comment so that you know what the correct answer was or what you missed. And then also for exam 4, when the time comes for that, I'll probably do a live session, something like this, to make sure, see what questions people have. I'm not entirely sure how all this is going to go, because I do want to go ahead and post as much as I can for you guys to be working on at your own pace, because I feel like some people might want to get this stuff out of the way, and some people might be, God forbid, but they might be sick, or they might be dealing with other stuff right now, so they might need more time. So if I end up posting like a video lecture or a demonstration of something, what I might do is then send out an invitation to say, like, join me live at this time and we'll go over that activity together. So you can do it on your own if you want to, but you can also join in to ask questions if you need to do that. So I will also do a review for exam 4. And for exam 3 and exam 4, I'll try to clarify what the correct answers are. Maybe I'll do a video for those. I'm just kind of playing it by ear. But feel free to email me your feedback on what you think I should be doing right now, because that would be really helpful. I'm not entirely sure. Any other questions? Thanks for your patience with all the technical difficulties and all of that, and the cat jumping around in the background. I appreciate that. That's all I have. So what I'm gonna do is pause the recording here, and then I will upload this. Canvas is a little slow today, but I'm gonna go ahead and upload this as fast as I can so that other people can see it. All right, I hope you're all staying safe out there, and stay well, and wash your hands, and practice social distancing.